In the last lecture, we talked about how we can impart charge to an insulator by simply rubbing, that is friction. In this lecture, we'll talk about imparting charge to a conductor by two methods, conduction and induction. In conduction, we are actually bringing two conductors in contact. Then, who decides how much charge will get transferred during conduction? And induction, we don't touch at all. So what is induction? We'll talk about it. And then how much and what type of charge will get induced? The study of electricity with conductors is by itself a very interesting topic. Then we'll go on to study an instrument called the Gold Leaf Electroscope, which is a device that can detect the presence of charge and also identify the type of charge. And while doing so, it makes use of a very important principle that repulsion between charges is a surer test of electrification. Welcome to the portals of real learning. Enjoy your learning. In the last session, we learned about how we can impart charge by friction. Such a simple thing like rubbing one body with the other, the friction is able to knock out an electron from one body and deposit on the other. Now the question is, how is it decided who is going to lose the electron? Either one could lose, right? On what basis is that decision taken? That decision is taken by electron energy levels, which translates to the attractive force that is there between the electron and the positively charged nucleus. If the electron is far away, that means the outermost electrons, it is far away, then it is easier to knock it out because it is attracted with a lower force. So that is what decides. So we have a question here. Up till this point, it is given that when A and B are rubbed together, then A becomes positive and B becomes negatively charged. If A and C are rubbed together, then A becomes negatively charged and C becomes positively charged. Question is this: if B and C are rubbed together, then who is going to lose electrons? Think of the tendency to gain electrons. Suppose I talk about A and B. When they are rubbed together, then B is getting the electron. So A is losing it. That means the tendency for B to gain electron is higher. That is why I have shown B higher than A. When I rub A and C together, then we can see that it is C that is losing the electron, right? These are the electrons that are lost. That means A is having a higher tendency to gain electrons than C. If I rub B and C together, then clearly B is having a higher tendency to gain electrons. So B will become negatively charged and C will be positively charged. Okay. Now let's talk about charging by conduction. And this will work for conductors only, whereas friction will work with insulator or with conductor. So here I have put a metallic ball on a rubber stand. The rubber stand is an insulating material. So any charge acquired by this metallic ball will not flow down to the earth. I bring a negatively charged metallic rod and touch it. Then charges flow from one to the other. The question is how much charge will flow? Will all the charge that is there, we are talking of the net charge. Remember, we are talking of the net charge. Will all the net charge on the rod flow or only part of it? What part of it? How is that decision taken? First of all, when you are doing charging by conduction, the same type of charges will appear in both conductors. But what is the magnitude of charge left after the process is completed? charges will move from one body to the other. And we are going to learn about this. They move due to a potential difference. The analogy is water flows from high pressure zone to low pressure zone. It moves due to pressure difference. Heat flows due to temperature difference. It flows from a hotter body to a colder body. When there's a temperature difference, heat flows. When there's a pressure difference, water flows. When there's a potential difference, charge flows. The concept of potential is very important to understand, which we are going to deal with later. That means charges will stop to flow when there is no potential difference. That is the fundamental point. When charge flow stops, it means that the potential of both bodies, they have become equal. On what does the potential of a body depend? It depends on two things: the amount of charge on it and the shape and size of the body. That is, its own charge will decide its potential, plus the charges that are around it will also affect its potential. A body acquires a potential due to charges on it as well as charges around it. If a certain charge is given to a body, then the potential it acquires is proportional to the charge. The potential that it will have will be proportional to the charge that was given to it, and it also depends on its shape, its size, and its material. If I talk of metallic sphere of radius r, and if I give a charge q to it, then the potential V is some constant into q by r. That means directly proportional to the charge given to it and inversely proportional to the radius. This is for a sphere, a specific example I have taken. So, if I have two identical spheres, metallic spheres, one had got a charge q initially and the other had no charge. When I connect them up, then charge flows from here to here until the potentials are equalized. So let us say some charge went from here to here, and the new charge on this guy is now q1, and the new charge on this is q2. But the total charge of the universe remains constant, and here we are only finding two bodies interacting. So the total charge now, that means at steady state, Q1 plus Q2 is equal to the original charge on the system. That is one equation. Second equation is equate the potentials. It is KQ by R. So KQ1 by R for this is equal to KQ2 by R for this. KR cancels. Q1 is equal to Q2. That means Q1 being equal to Q2 and the sum being equal to Q, that means each Q1 and Q2 is Q by 2. So the final configuration is that both of them will have equal charge Q by 2, Q by 2. This happened because their radii were equal. If I take a different scenario, Q on this, 0 on this to start with, but the radius here is R and the radius here is R by 2. So charge will flow from here to here until the potentials are equalized. So again, by charge conservation, Q1 plus Q2 is equal to Q. This is the steady state situation, and equate the potentials. KQ by R is equal to KQ by R. This is KQ1 by R, but this is KQ2 by R by 2. So KR cancels, this 2 goes there. So Q1 is equal to 2Q2. Q1 is equal to 2Q2. So if I replace the value of Q1 as 2Q2, then Q2 plus Q1 is Q2 plus Q1. This is Q1 is equal to Q. That means Q2 is Q by 3. And Q1 is double of that, 2Q by 3. So the charge that it had doesn't now distribute equally. Only 1/3 goes to the other guy and 2/3 remains here. So the final configuration is 2Q by 3 and Q by 3. So that answers the question, how much charge will flow from one body to the other if they are placed in contact. They will flow until the potentials become equalized. The other method is charging by induction of a metallic body. So I have the same metallic body on a rubber stand, and I bring a negatively charged body. It may be a conductor, may not be a conductor, but I just bring a negatively charged body, but don't touch it. I bring close to it. In a metal which is a good conductor, there are mobile charges. And for metal, though, the mobile charges are only the electrons. So if you bring a negatively charged rod, the electrons will get repelled and they'll come to this side. They can't leave the body. They don't have so much energy to leave the body. So they'll come to the right hand side. Movement of electrons from the left to the right implies there's a scarcity of electrons on the left hand side. And a scarcity of electrons is equivalent to presence of positive charge. Loss of an electron means acquiring a positive charge. So there's a deficit, there's a scarcity of electrons on the left hand side. So the situation is this. Now, if I remove, while it is the situation, if I remove the rod, take it far away, then there's no reason for the positive and negative charges to remain separated. They will attract each other and be back to square one. Please remember that net charge on this guy is still zero as of now. It was neutral to start with. The process of induction means redistribution of charge. Induction means redistribution of charge within the body. There is no charge given to it or taken away from it so far. From this situation, if I touch this part with my hand, my foot is in contact with the ground, and I'm not wearing rubber boots, I'm barefoot, so there's a circuit, there's a connection that I'm giving. Electrons were getting repelled, right? But they could not leave the body. If I touch it, then I'm giving them a path. They will say, "Thank you very much. I was being repelled by this guy. You are giving me a path to go to the Mother Earth." So these electrons will rush to the ground and enter the Earth. But these positive charges are still held in attraction by these negative charges around here. So that is the situation. After that, if I remove my hand, so this connection is gone, then this body has got a net positive charge. We have imparted charge to this metallic body by induction. There was no contact made with this negatively charged rod. Furthermore, if I now remove the negatively charged rod, take it far away, then there's no reason for all the positive charges to remain concentrated on the left hand side. They are repelling each other. So they'll go as far away from each other as possible. But they don't have sufficient energy to leave the body. So what will they do? They will all go and distribute themselves in some manner within the body. And if it is a metal, if it is a good conductor, then all the charges will be sitting only on the surface. There'll be no charge inside the conductor. That is the first thing, all on the surface. Second, if it is such a symmetrical body where the radius of curvature here is equal to the radius of curvature here, everywhere the radius of curvature is the same, then the charge per unit area on a small area that you take, the charge density per unit area will remain uniform. So all the positive charges they are going to distribute themselves uniformly. We observe that during the process of charging by induction, opposite type of charges will be created here by this process. But in conduction, it was the same type of charges. Let us do a small question on these concepts. A, B, and C are three identical insulated spherical conductors. A and B have some charge and C has some negative charge. A and C are touched and then pulled apart. After that, B and C are touched and pulled apart. Now, if A and B are brought close to each other, would they attract or repel? If A and C are brought close to each other, would they attract or repel? So let us draw the picture A, B, and C. They are identical means the radius is the same. And we have learned that if you have two identical spheres and one guy had some charge, other guy had zero charge, when you bring them in contact, then the final configuration is equal charge on both. So A and B have got plus 3 coulomb charge and C has got minus 6 coulomb charge. So first A and C are touched and pulled apart. Okay, so if I touched them, then both of them will acquire the same charge because they are identical. And the sum of the charges on the system will remain the same. What is the sum of charges? Minus 6 and plus 3. So the net charge on the system of A and C is minus 3 coulombs and they will have equal, so half of that. So that is the situation when you touch A and C, minus 3 by 2 and minus 3 by 2. After that, B and C are touched and pulled apart. Okay, so let's touch B and C now. Between B and C, the net charge is plus 3 minus 3 by 2. That is plus 3 by 2. Net charge on B and C is plus 3 by 2 coulombs. After the contact is made, both of them will have half of that. So this will go to plus 3 by 2 was there. This will now have plus 3 by 4 coulombs. And this will also have plus 3 by 4 coulombs. So the final situation is A is this much, B is this much, and C is this much. If you bring A and B together close to each other, they are opposite charge, so they will attract. If you bring A and C together, or rather close to each other, again they will attract because they are of opposite signs. So this problem demonstrates how charges are transferred and how much charge is transferred. One very important thing to understand is repulsion is a true test of electrification, meaning that whether a body has got a charge or doesn't have a charge. See this scenario. I have two identical metallic balls. One is having plus Q, one is having 0. And I don't touch them. I just bring them close to each other. Then induction happens here. Negative charges are electrons are attracted, creating a deficit of electrons. So I'm going to use the term positive charges move to the right and negative charges move to the left. But be very clear that metals don't have any mobile positive charge. It is only electrons. But a movement of electron to the left implies creation of positive charge on the right. So that is the situation. So induction has happened. Now what will happen? These guys, there'll be attractive force here and there'll be repulsive force here. But the negative charges are closer, therefore the attraction will be more. So there is an attraction between the two. If you bring a charged body and an uncharged body close to each other but not touching. But same thing will happen if the two bodies have opposite charge. Attraction is going to happen. So if I only told you this much, that there are two bodies, when I bring them close to each other, there is an attraction between them. If I only told you this, then you cannot conclude that both of them had some charge on themselves. It is possible that one is positive, one is negative, or it is possible that one is positive and one is 0. This experiment does not conclusively demonstrate that a particular body was having a charge or not. But if I bring two identical spheres with identical positive charge, then they will repel. Repulsion cannot happen unless both of them have charge, either both positive or both negative. But both of them have to have the charge, otherwise repulsion will not happen. So if repulsion happens, then we can definitely conclude that both of them had charge, and also we can say that both of them had the same type of charge. We can't say positive or negative, but same type of charge. So repulsion is a surer test of electrification. Attraction is not a sure test. And for all of this, we have a very nice instrument called Gold Leaf Electroscope. The actual picture of the instrument is given here. It is used to detect small charges on a body and also to find the nature of these charges. Look at this picture, which describes the entire instrument. There is a thin gold leaf that is placed here. Gold is highly ductile and malleable, so we can make very thin and light strips. It should be light because the forces that are involved are going to be tiny and you want to observe something, therefore, the weight of that gold should be very small. So, very thin strip should be there. And that is connected to a metallic rod. This is metal, and there's a metal cap also here. There's an insulating piece between these two. All of that is placed, the gold leaf is placed inside a box in which there's vacuum. We don't want any interference with air molecules also. And this whole thing is earth. The earth means connected. This is a symbol for earth. Connected to the ground means any outside charges out of this box is not going to affect what is going to happen inside. This is called shielding. A metallic cage, which is earth, acts as an electrostatic shield so that it is protected from the influence of any charges outside. Now, let us use this instrument to detect the charge. So I'm only showing the metallic cap and the metallic stem and this gold leaf, which is yellow in color. There's no charge, so the gold leaf on its own, it is hinged over here, will be hanging vertically down due to its own weight. Now, suppose I bring a negatively charged rod close to it, then induction will happen. Positive charges will be created on the metallic cap, and negative charges will go to the opposite side, including the gold leaf over here. So, negative, negative both sides. So, therefore, there is going to be a deflection of the gold leaf by some angle and it will stay like that as long as it is kept here. Once again, just look at this animation. We brought a negatively charged rod. Induction happens. Positive charges appear here, negative charges are repelled, come here, and they also go to this gold leaf electroscope. So, therefore, it is experiencing a greater repulsion from these charges rather than the attraction by the positive charges far away. Therefore, there is a deflection. Now, this amount of deflection is dependent on how much charge there was on this rod. More the charge on this rod, greater would be the repulsion. That means this angle would be larger. All right. So this indicates if initially the gold leaf electroscope was uncharged, even now it is uncharged. Induction only means redistribution of charge. The entire equipment, the electroscope was neutral, it is still neutral. But this deflection that happens indicates that this rod had some charge. Whether positive or negative, we still can't say. Even if you brought a positively charged rod, this deflection would still happen. The only difference is negative charges would appear here and positive charges would appear here, but the deflection would still happen. So we can only detect the charge. We can say that this particular rod had some charge on it. Now, let me just erase these things. Very interestingly, the rod still being there, if I touch the metal cap now, that means I earth the metal cap, then positive charges are still held in attraction, they can't leave. But the negative charged particles, they were being repelled, they will say, thank you very much, you're giving me a path to go to Mother Earth. The repelled electrons, if we touch the metal cap, the repelled electrons will go into the Earth. That means the electroscope has lost negative charge, so it becomes positively charged. And if we now remove this rod, then the positive charge created due to induction will spread all over the place within the electroscope. These negative charges will not be there, they have all gone out. But then the positive charge that was created will get distributed everywhere and the leaf will stay repelled. So I hope you have understood the process. Now, let us use this instrument to identify the type of charge. For this, we need to have an electroscope that is already charged. And we just saw how we can create a positively charged electroscope. Okay, so we start from there that we have created a positively charged electroscope. The gold leaf is already repelled to some extent. Now, if I bring a negatively charged rod, what will happen? This electroscope has got net charge, right? So if a negatively charged rod is brought close, then all these positive charges are going to feel the attraction. So some of these charges which are sitting on the metallic stem as well as on the leaf are going to rush this side, leaving fewer charges at the leaf. Therefore, reducing the repulsion and the deflection will reduce. If I brought a negative charge, see, we have already created a positively charged electroscope. We know the type of charge on the electroscope. We know it is positive. I bring a rod which is said to carry some charge on it, and if I bring it close and I find that the deflection of the leaf is reducing, then it must mean that the rod was negative. So we can identify the type of charge. But hang on, let us discuss another scenario. This attraction is not a true test of electrification. If the rod was neutral also, suppose the rod was neutral and you bring it closer, then this positive charges sitting on the electroscope would have induced this negative charges on that rod. And the same process would continue and the deflection would get reduced. So we need to just sit back and then analyze. If I already have a positively charged electroscope and I bring a rod close to it and I find the deflection reduces, then there are two possible conclusions, not one. One possibility is that the rod was negatively charged, and the second is that it was neutral. But repulsion is a surer test. If a positively charged rod was brought close to the electroscope, then the deflection would increase. Why? A positive charge here is going to repel the guy's positive charges that was sitting on the metallic cap, and the reverse traffic would happen, increasing the charge on this side. Therefore, the deflection would increase. Thus, with a positively charged electroscope, GLE means gold leaf electroscope, if we get more deflection, we can definitely say this time that the rod was positively charged. Repulsion is the surer test for electrification. So the gold leaf electroscope can be used to detect charge and also to identify the type of charge. In the next session, we are going to learn about what is a force between two charges, what is the law behind it, and we'll also do some numericals on that.